All right, guys, welcome back. What we're going to discuss today is something called the ideal gas law. The ideal gas law is basically a mathematical representation in real time of pressure, volume, the number of moles, and something called the ideal gas constant and the temperature. Whereas in the combined gas law, we were looking for a change, right? We were looking for what it was and what it will be. We had P1 and P2 and V1 and P2. You guys get the idea. We had two different scenarios, what it is and what it will be. In the ideal gas law, it's not like that at all. So we're not going to be given two pressures. We're not going to be given two volumes. We're not going to be given two of anything. We're only going to be given one of each, except of course one is going to be missing, which is what we're going to be solving for. So that's an easy way to determine which type of problem is a ideal gas law versus what you already know of the combined gas law. Again, just to repeat, you'll only be given one of each. So one pressure, one volume, one number of moles or quantity of gas particles, and one temperature. Again, one of those will be missing, of course. All right, so the way it looks is PV equals nRT. Now, what you see at the middle of your screen, it says R, PV equals nR. R is the ideal gas constant. It is a number that people have determined experimentally, and there are three forms of them. So let me go ahead and show you what I'm talking about. There is one right here, there's one right here, there's one right here. Now, the only difference between these three, if you look at it really closely, they both have volume, they both have a pressure, moles, and temperature. The only difference, notice, is the pressure unit. So whenever you're using these R values, you want to pick the one that has the correct pressure unit. So if your problem has ATMs, then you're going to use 0.0821 liters ATMs over mole Kelvin. If you're given a pressure unit in the problem that is in kPa, then of course you would use 8.31 liters kPa over mole Kelvin. And of course, you understand the idea for the millimeters of mercury. So you're going to use the appropriate R value depending on the pressure unit. Now, what that also means is that you're never going to be asked to actually solve for the R because the R is a constant. Why would they ask you to solve for a constant? So that will always be known, but never really provided in the question. You, again, just need to know what it is and where to find it. So that takes me to my next point. Where you're going to find it, of course, is if I go into the formula chart, here we are. What you'll notice right here is, of course, our ideal. Whoa, I'm drawing a line on accident. Didn't mean to do that. The PV equals nRT. There it is right there. Pressure, volume equals the number of moles, the ideal gas constant, and temperature in Kelvin. Must be in Kelvin. Okay. Again, right above it is the Dalton's law of partial pressure. Right below it is the combined gas law, which we have already practiced. If I go on to the next page, again, what I want to draw your attention to is right here. We have our R values, excuse me, R, or the ideal gas constant. That's kind of hard to say. So again, here's one there for your ATMs. Here's one here for your kilopascals, or one here for your millimeters of mercury. So those are your three R values. Again, they are provided for you. You always have them. As always, you do not need to memorize them. All right, all that being said, let's go ahead and get into some practice. So for this, what we're going to do is start with number one, obviously. So number one, what we have here is what volume would be occupied. So let me pause there. Obviously, we don't have a volume, so that's going to be our X, our unknown, our variable. What volume would be occupied by 0.625 moles? Again, that's going to be our N. Here's our volume of hydrogen at 4 atmospheres. That's our P. And here's our T. So we just need to put that in the right place. Now, as I do that, remember, as long as these are side by side, it doesn't matter if pressure is first. As long as I put these side by side, it really doesn't matter, although I do like to do those in order just to make sure I don't forget them. But pressure and volume, again, it doesn't really matter. But I'm going to go ahead and do it in order for this time. So our pressure is 4.00 atmospheres. Our volume, again, we don't know it, equals our number of moles, which is 0.625 moles. All right, and then we need an R value. So our R value, notice our pressure is in atmospheres. It's in atmospheres. So I need to use the one that is in atmospheres. Again, there's atmospheres. So 0.0821 liter ATM per mole Kelvin. All right, then I need to get my temperature in Kelvin. So I'm going to add those together. That would be 310. Yep, Kelvin. Now, again, the units right here, everyone always asks me this each year, like, what the heck is all that, right? Again, those are just the units. If you were to actually solve for R, say if they actually asked you to do that, which again would be a silly question to ask you since we gave you the answer, but if they did ask you to solve for R, you'll notice that nothing cancels out. Absolutely nothing cancels out. So you would be left with liters ATM, which is the left side of the equation, ATM in volume, over mole Kelvin, which is on the right side. Again, nothing cancels out, so it becomes liters ATM over mole Kelvin. Now, if I solve for anything else, they're all going to cancel out except for the variable that we're looking for, and you'll see what I mean in just a second. So I'm going to pick up my calculator. Before I do, algebraically, you guys know that if I have my V or my X over here, I need to get rid of what's next to it. Again, you guys know this. This is just algebra. So I'm going to do the same thing to this side, because if I do it to the left side, I have to do it to the right side. That will cancel that out, right? So that means V equals all that mess to the right. So I'm going to pick up my calculator. I'm going to do 0.625 times 0.0821 times 310 divided by 4, and I get 3.977. Again, so let's just double check. So we have moles here and we have moles there. That cancels. I have Kelvin here, and I have Kelvin down here. Those cancel. I have, this would be, again, ATM. I have ATM down here. I have ATM up there. That cancels. What am I left with? Liters. So, again, the volume is always going to be in liters, okay? Again, notice liters, liters, liters. The temperature is always going to be in Kelvin, and it must be in Kelvin because, again, that's what the R values are. Moles obviously is going to be moles. Again, it comes down to the pressure unit. That's the big question. All right, so that's how you do number one. Again, it's just you have to put it in the right place, do a little bit of algebra in order to solve for our unknown, and you're good to go. So let's go ahead and try number 2. So number 2, what we have here is how many moles of gas fill a 2.2 liter vessel, which is a container, with a pressure of 1.2 atmospheres at 25 degrees Celsius. So again, notice we've given one volume, one pressure, one temperature. That cannot be a combined gas law, because we would have to have two pressures or two volumes or two temperatures or something to that effect, right? So I'm going to go ahead and put these in the right place. So I have 2.2 liters. I have a pressure of 1.2 atmospheres. Notice that's the opposite of this in order, but it doesn't matter. Equals my number of moles. Well, I don't know my number of moles, times my ideal gas constant. Notice my pressure is in atmospheres, so I'm going to use the exact same one as before, 0.0821 liters ATM mole Kelvin. Whenever I say it out of habit, I always say ATM liters per mole Kelvin as opposed to liters ATM per mole Kelvin. But remember, as long as they're side by side, it doesn't matter. That's just the way I've always said it. So to change my temperature, I'm going to add 273 to my 25. Again, doing this in my head, which always scares me because I'm doing this live and I'm probably going to make a mistake and make a fool of myself. Nope, I think I'm pretty confident on that one. 298 Kelvin. So again, what we're going to do is we're going to have some numbers here. N is our unknown, so we need to divide this by 0.0821 and also by 298, which will cancel that, which will cancel that. But if we do it to the right side, we better do it to the left side, so 0.0821 and also 298. So that means when I'm finished, N is going to equal, let's find out, 2.2 times 1.2 divided by 0.0821, divide again by 298, all in one step. You know how I like to do this. 0.108 moles. There's our answer. Okay, so in a way, this setup is a whole lot easier than the combined gas law because you don't have to read quite as carefully to figure out, are we talking about the changed conditions or the initial conditions? And we don't have to figure out, okay, what are we going to leave out? Do we have no temperatures? Okay, cancel out temperatures and ignore it. This is much more straightforward in that you will be given all of them except R, because again, it's a constant. They're not going to give you the constant. And you're going to be missing one of the other four. But really, again, the setup is quite simple. The algebra part, I guess, could be a little bit confusing for some. All right, number 3. What volume, so that's our, again, our unknown, would be occupied by this many moles at a gas of that temperature in this pressure? So PV equals nRT. P is 740 millimeters of mercury times my volume, again, I don't know that, equals N, 0.50 moles times my R. Now, real quick, it's millimeters of mercury. That's a different than atmospheres. I don't have this one memorized. Millimeters of mercury, again, here it is. Oops, I just completely moved it. That was totally unintentional. Go back. It's not like I'm doing this, first live for the first time, right? Anyway, so there's our millimeters of mercury right there. So I need to use 62.4, 62.4. All right, so let's go ahead and go back. All right, so I'm going to add or multiply 62.4. That would be millimeters of mercury, liters per mole Kelvin. Again, those are just units. And then my temperature is right here, 25 plus 273 would be 298 Kelvin. Okay, again, I have my V or my X over here, so I need to divide both sides by 740. That will cancel. And I need to do the same thing over here, divide both sides or that side by 740, picking up my trusty companion. I'm going to do 0.5 times 62.4 times 298 divided by 740. And my final answer for my volume comes out to be 12.564. And again, it's going to be in liters because our R is in liters. So again, we don't have to guess the units. Just look at your R value, the units behind the R value, and it'll tell you what your unit's going to be. Okay, number 4. Let me change my colors because you know how I am. What volume would be occupied by, again, what volume? Why are we always solving for volume? Would be occupied by, this is grams, of hydrogen at this pressure and this temperature. Interesting. So they're really throwing us a curveball here. What we're missing is we don't have the number of moles. Well, guess what? We're going to have to do a little conversion to figure that out. So what we're going to do is we're going to start with our 5.0 grams of H2. We need to convert into moles. So I'm going to put the molar mass of H2 down there and moles of H2 up here. You know that for every molar mass of hydrogen is going to be equal to 1 mole. The mass of hydrogen is 1.008 off the periodic table behind me. If I multiply that 2, because again, there are 2 hydrogens in a molecule of hydrogen, that would be 2.016. Again, it's just the mass of hydrogen times 2. Then that will cancel, and my answer will be in moles of hydrogen. Then we'll be ready to do the ideal gas law. 5.0 times 1 divided by 2.016 and 2.480 moles of hydrogen. So there we go. Now we have all the numbers that we need. Now we're finally ready to do the ideal gas law equation. So we have our volume, again, is unknown. Our pressure is 410 kilopascals equals the number of moles. Well, we just calculated the number of moles. Oops, I can't write it though correctly. 480 moles. Then I need my R value. Now notice our pressure is in kilopascals. Well, again, I actually honestly don't have that memorized. So kilopascals is 8.31. 8.31, again, let me just show you. Kilopascal, oh my gosh, why do I keep messing up? Kilopascals is right there, so it's 8.31. That's what I was talking about. Okay, scrolling back down, number 4, and right about there. So we had 8.31. Again, that would be kilopascals liters per mole Kelvin. Then I'm going to have my temperature. My temperature, again, is 273 Kelvin plus 30 degrees Celsius. That comes out to be, again, 310 Kelvin. All right, so again, not surprisingly, I'm going to divide this side by 410, which cancels that out. Divide this side by 410, and my volume for my gas at the current conditions, not changed conditions, but my current conditions, is going to be 2.480 times 8.31 times 310 divided by 410 equals 15.582 liters. That is our volume, current volume of hydrogen gas given the mass of grams. So we had to do a conversion, think of unit 6, unit 7, to convert those grams of hydrogen into moles of hydrogen. All right, so that was just a little bit of a curveball, but again, hopefully we all remember how to do that. Hopefully you guys, your brains didn't explode or you didn't start crying in the middle of that problem. All right. Well, guys, that's it. That's the ideal gas law, okay? Again, the main thing is you need to use the appropriate R value called the ideal gas constant, solely dependent on the appropriate gas pressure, okay? You use the one that matches the problem. Otherwise, you could convert for example, you could convert atmospheres into millimeters of mercury, but that's not really necessary. Again, these are all provided to you on the formula chart, okay? All right, guys, as always, thank you for watching and learning about the ideal gas law.